Hi everyone, welcome back. In this segment, we're continuing with examples on integration by parts and specifically examples involving the natural log function. So let's begin with the very basics, which is just ln x all by itself, not multiplied by anything, just integral of ln x dx. Now, some of you may say, haven't we seen this already? Isn't this 1 over x, right? Well, the answer is no, we have not seen this already. All we have seen before is the derivative of ln x, which is equal to 1 over x, right? So to integrate ln x, we need to come up with a function. When differentiated, it gives you ln x. So like you want the answer to be equal to ln x when you are differentiating this quantity, and that we don't know. We haven't seen such a function yet, okay? So therefore, we're going to try to use integration by parts. So this is a little bit unusual example because typically we use integration by parts for things that are of the form of a product, but it can also be applied to sometimes just a standalone function. So let me show you. So let u be equal to ln x and dv be equal to dx. So again, now we wrote it in the form u dv, and we know formula states uv minus integral of v du. Okay, so for that we need to know what v is, we need to know what du is. So du is the derivative of ln x, which is 1 over x dx. And v is the entire derivative of dx. Think of it as 1 dx, entire derivative is x. So coming over here, integral of uv, you're going to multiply ln x times x, minus integral of v du, you're going to take the integral of this product, x times 1 over x dx. And notice what happens there. The x times 1 over x, they cancel out. So leaving the first part as it is, you are left with minus the integral of just dx. Think of it as 1 dx. So here we have x ln x minus the integral of 1 is x and plus c at the end. I can also leave this as x times, factor out the x, ln x minus 1 plus c. So that is the entire derivative of ln x. Typically we remember it like this, x ln x minus x plus c. Now what happens if you have limits of integration, such as this given same integral, but this time from 1 to 3. So first step, you would forget about the limits of integration. You would do everything we did above. So you would find the entire derivative, which is x ln x minus x. And at that point, instead of putting the plus c, you draw a line. We're going to evaluate it from 1 to 3. So at this point, I'm going to plug in the upper limit everywhere I see an x. So 3 ln 3 minus 3, minus plug in the lower limit everywhere you see an x, and you can have 1 times ln 1 minus 1. Now ln 1 is 0. So here you have minus 1, another negative, it gives us a plus 1. And here we had 3 ln 3 minus 3. So if you simplify the minus 3 plus 1 at the end, we can leave this as 3 ln 3 minus 2 as our final answer. So if you have limits of integration, just wait until the last step when you bring the x's in, and just like before, instead of putting the plus c, you would go ahead and plug in the limits, upper limit minus the lower limit. Okay, now that's if ln function appears all by itself. Okay, but sometimes you're going to see the ln function together with a power of x. So for example, something such as this one. Okay, the integral of x to the third times ln x. So here we could try, to select x cubed to be the u, or we could try to select ln x to be the u. At that point, if you try, like, again, you have two options, right? So if you let u be x cubed and dv be ln x, so when you get here, from here to here, you have to integrate. So just to get the integral of ln x, you have to use integration by parts. And it gets actually more complicated, not any easier, right? So this doesn't seem like it's going to work out so well. Let's switch it around. So this is a little bit unusual. Usually when we have power of x, we like that to be u, right? But when it's together with a natural log function, it actually helps to do the opposite. So let u be ln x and dv be x to the third. So du is 1 over x dx. And from dv to v, you take the antiderivative, which is x to the 4 over 4. So this is going against everything we've said so far, right? It's getting more complicated, but just wait to see what's happening when you also have natural log function in the equation. So this integral is equal to u times v, the product of x to the 4 over 4 times ln x, minus the integral of v du. So that's 1 over x dx times x to the 4 over 4. So you see what's going to happen here is things actually are going to simplify nicely. So inside that integral, let's go ahead and simplify it a little bit. So first of all, the 1 over 4 part, I can take it outside. And the x to the 4 over x, inside the integral, that'll be x to the 3rd dx. And now you see this is going to be easier to integrate, certainly easier than the original question that we had to begin with. So we're going to have x to the 4 over 4 ln x minus x to the 4 over 4 is the antiderivative of this, but don't forget the negative 1 over 4 sitting here. So that's going to be negative 1 over 16 x to the 4, because x to the 4 over 4, that the 4's in the denominator will get multiplied, right? And then plus c. So we could certainly factor this out a little bit. You know, we could put out the 1 over 4x to the 4 and then write everything out. But it's okay. Usually, typically, we're not solving an equation. We're not going any further. So it's okay to leave these in this format as well. So in other words, something we've learned from this example is when you're integrating a function of the form x to the n times ln of x, we did something unusual. We let u be equal to ln x, not u equal to the x to the power. Okay, so that's something to remember through the next few examples in this segment. So let me see. All right, so here's another example involving the natural log function. We have the square root of x times ln x. Again, technically this is of the form x to a power times ln x. We're going to apply what we just learned. Let u be ln x and dv be the power of x. So let u be ln x and dv be x to the 1/2. In this case, square root of x, same as x to the 1/2 dx. Now, u to the u we differentiate, we get 1 over x dx. Okay, dv to v, we're going to anti-differentiate. It's going to be x to the 3 over 2 divided by 3 over 2, or 2/3 times x to the 3 over 2. And applying the formula, is going to be u times v, so multiply those two together. So 2/3 x to the 3/2 times ln x, minus integral of v du, so integrate the product of these two. So minus the integral of, and you can take the 2/3 outside of the integral sign. It'll be 1 over x times x to the 3/2 on the inside. Okay, before you attempt to integrate this, simplify it first. So there you're going to need to subtract the exponents, right? Think of it as x to the power of 1, and there's x to the 3/2, so the 3/2 minus 1, which will be like minus 2 over 2. You're going to have just 1 over 2, x to the 1 over 2, right? So let's write that out. The first part is unchanged, copy it over. Second part, you were simplifying what's inside the integral. We have the integral of x to the 1/2. So at this point, we're going to be integrating x to the 1/2. Notice it's so much easier than integrating the original question, right? So that'll be x to the 3/2 over 3/2, or times 2/3. There's already a 2/3. It's going to be another 2/3. It'll be 4/9. So the first part is unchanged. The second part, the negative 2/3 is sitting there. The entire derivative is x to the 3/2 times 2/3. So the final answer will have a minus 4/9 in front of the x to the 3/2 term in the last answer. So the first part is unchanged. I'm just copying it over. Second part is minus 4 over 9, x to the 3/2 plus c. So another similar example to the last one, where we had to let u be ln x and dv be the power of x. All right, one more example involving the natural log function together with a power of x. And here it is, the integral of ln x over x squared dx. Okay, you might say, can't I use u substitution for this, like let u be x squared, but there is 2x dx. there is ln x dx on the top, but not an x dx, right? Therefore, we really could not use u substitution for this. But what we can do is we can rewrite this integrand as x to the power of -2 times ln of x. And now it's of the form, just like the last two problems, right? So let u be equal to ln x, and let dv be equal to the power of x dx. So here you differentiate, you get 1 over x. Here you anti-differentiate, so you're going to have to add 1 to the power to get x to the -1, divide by -1. That's the same as multiplying by -1, right? In other words, you're getting -1 over x plus c. Now applying the integration by parts formula, u times v will be ln x times -1 over x minus integral of v du. So we're going to multiply these two together minus the integral of v du. This times that is going to give you -1 over x times -1 over x. That's -1 over x squared dx. And the negative times negative is positive. So let's simplify that a bit. And how do we integrate 1 over x squared dx? Well, put it on the top as x to the -2 and then apply the power rule, basically just like we've done it over there, right? So the integral of x to the -2 will be x to the -1 over -1. The first part I'm copying it over. The second part will be basically -1 over x plus c. So if I want to factor it out, I could take out a -1 over x, and that will leave me with ln of x plus 1 with the plus c on the outside. Again, you can leave it on either format, that will be fine. And what if you had, as a part B to this question, limits of integration? Same question, but you're integrating it from 1 to e. So in that situation, I would say just take it from this point or that point where you're going to plug in the limits. So let me just take it, doesn't really matter. Let me take it from this point. So I have -1 over x ln x minus 1 over x, and we're going to go from 1 to e, starting with the upper limit. Plug in an e, so you're going to have -1 over e. ln e is 1, so I'm going to put a 1 for that, minus 1 over e. Minus, plug in a 1. Now ln 1 is 0, so that times anything will be 0. And then minus 1 over 1. So the two negatives at the end give me a positive 1. And -1 over e minus 1 over e. So that's like -2 over e. So I could leave it like this. I could convert it to a decimal point. And I could even get common denominators, but I think this was perfectly fine to leave the answer as 1 minus 2 over e. So in this segment, we've seen a variety of examples involving natural log function. So we learned that it's the reverse. Instead of letting u x to a power, we let u be ln x when you see the natural log function together with as a product with an x to a power. Okay, in the next segment, we're going to finish up a few weird examples in integration by parts, things that maybe you wouldn't have thought that can be done with the technique, but we'll be able to do it, such as inverse trig functions.